Physics 1.2c. Finally, hopefully we can get through this physics topic. So, as per usual, in your syllabus, you should be writing out each point and then taking notes as you go. So we're going to start here, calculate the area under the speed time graph to work out the distance traveled. So, here we go. Alright, so we're gonna construct a speed time graph. Alright, and we're going to do an easy one to try and get this through. So let's say I run at a speed of 15 meters per second for 5 seconds. So I end up with a line that looks like that. Okay? And then I come to a complete stop because I run straight into the wall. My question is, how far did I run? Now your first option is to take a peek at your magic triangle, which has speed equals, which has, you cover up what you want, and your formula is speed equals distance over time. I don't want speed, I want distance. Why am I not paying attention? So, without looking completely retarded, okay, never made the mistake. So, when you use your magic triangle, you see that distance equals speed times time. And you could work this out. Look at your speed, look at your time, fill it out. But what if I asked you, what is the formula for area? And you would say, especially area of this shape right here. Bang. The area of that shape is going to be, you know, length times width. And what do you know? The length is the time, and the width is the speed. So what we actually see is that distance is equal to the area of a speed time graph. Okay? And the area can be different shapes. Let's say, for example, I have a graph that looks like this. So I have a graph that looks like this. The question now is, can I work out the area of this graph? I sure can. I think you guys do stuff like this in P6 or something. You take this shape and you break it down into shapes that you can work out the area for. And, you know, give them some labels, A, B, and C. Now the question is, can you work out the area of A? Sure can. Boom. You know the area of A, that's a triangle. Your formula is half base times height. B is a square, it's length times width. C is another triangle, half base times height. Add A plus B plus C, and you have total area. So instead of actually using the formula, which would be rather difficult, speed times time on this one, because the speed's changing, you just work out the area. Whenever you're given a graph with the speed and time, and you're supposed to work out the distance, they want you to recognize that distance is equal to area. Okay? And you work it out using whatever formula would work for that situation. Planet Earth, also known as, you know, Earth. Fine. So, planet Earth. If you jump out of an airplane, so you have an airplane flying above Earth, and you jump out, and then someone threw your luggage off the back. In a perfect world, you and the luggage will land at the same time. And in this case, you don't have a parachute, so maybe it's not so much of a perfect world. And that's because everything falls at a constant acceleration near Earth. Gravity is what causes you to accelerate, and gravity is the same for everyone. The reason why some things fall faster or slower than others has to do with wind resistance. If I was to drop a penny and a feather from the Empire State Building, the reason why the penny hits the ground first is because the feather is going to float because of the air pushing against it. But if I was to take those two and put them in a vacuum, if I was to put them both in a vacuum, so airtight but no air is inside, so I put them in a tube and I suck all the air out, they'll actually fall like rocks, both of them, the feather and the penny. Google it. No, don't Google it. YouTube it. Penny and feather in a vacuum. It's true. So the reason why the feather falls slower is because there's a bunch of air particles in the way that it hits and slows down. Think about trying to run through the corridors when it's full of people versus the penny, which has a small area, so it doesn't hit as many people and it falls straight through. But on Earth, everything falls at the exact same acceleration, and that number is 10. Okay? So everything falls at this 10 number. In 1 second, a penny is going 10 meters per second. In 2 seconds, it's going 20, and you keep adding 10. In a vacuum, a feather would do the same thing. So, just to be annoying, if you had 10 grams and you had, I don't know, that much, 1,000, million, a billion, gajillion, zillion, they would both hit the ground at the same time. After 1 second, they would both be going 10 meters per second. After 2 seconds, they would both be going 20 meters per second. And after 3 seconds, they would both be going 30 meters per second. They will all speed up at the same rate all the way until they hit the ground, if this was a vacuum. And you guys know this to be the fact. When skydivers jump out of airplanes, you know, the first thing they do is they open their arms and legs. But let's say he dropped his cell phone. What do? They put their arms and their legs straight like a little bullet, and then they go down a lot faster. That's to change the air resistance, right? There's less air blowing against them. Terminal velocity has to do with the acceleration due to gravity matching the force pushing up from air resistance. And the way to think about that, let's say you have two identical people with the same amount of strength, same people, these are twins, alright? And one is pushing a shopping cart full of rocks, and the other one's pushing an empty shopping cart. They reach their terminal velocity based on the resistance. So they'll both get to a point where they can't go any faster. He'll be pushing as hard as he can, and he's going, 35 kilometers per hour. He's going the speed limit. But if this guy's pushing as hard as he can, and they're the same person, he can get to 50 kilometers per hour. Both of these guys are at their terminal velocity where they can't go any faster, but this is different due to the resistance, which in this case is the weight of the shopping cart. But if we talk about our skydivers, please have a yes. Terminal velocity has to do with the air resistance, which is the air particles in the way which effectively are pushing up. So if one guy opens his arms up and the other guy, why would you do his head that way? And the other guy closes his arms and makes himself like a bullet, the amount of air resistance is going to be different for each one. He's going to hit a lot more. So his terminal velocity, he will fall slower. He will reach terminal velocity a lot faster. This guy is going to fall very fast because he's only going to hit these 4 molecules. This guy's going to hit 10, 20, 30. He's going to hit every molecule in the sky. That's what parachutes do. Parachutes are huge, and what they do is they hit lots and lots of air molecules. Why are they so big? Which push up. There you go. Causes it to slow down to almost nothing. Okay, so let's take a peek at the syllabus. I think we're done. Ooh, I should go and do it this way. Can you calculate the area under speed time graph, work out the distance travel? Yes. Please note it says with constant acceleration. They're not going to ask you to work out a speed time graph, distance travel of a curve, or non-constant. They want you to use the length times width and all that type of stuff. Demonstrate some understanding that acceleration is related to changing speed. We did that the other day. If you speed up, you accelerate. If you slow down, you accelerate negatively, and we call this deceleration, okay? State that acceleration of free fall for a body near to Earth is constant. Everything near Earth falls at a constant rate. We know that that number is 10. Whatever units come up in the question, just know that the number is 10. Describe qualitatively, meaning try to talk about it. The motion of bodies falling in a uniform gravitational field with and without air resistance. You know, without air resistance, they all fall at the same rate. And with air resistance, they reach their terminal velocity. Okay? Done. Every time. I swear, man, you have one job.